limit of the integration is of type minus a to a, so this integral becomes 0, and therefore the inner product of p and q, the vectors x and x square of p2 is 0, and so we say that they are orthogonal relative to the given inner product. Next is generalized theorem of Pythagoras. So if u and v are orthogonal vectors in an inner product space, then square of norm of u plus v is equal to square of norm of u plus square of norm of v. Let us have proof of this on Teletop.
Start कर दो.
So we are given that u and v are orthogonal. That means inner product between u and v is 0. Now let us start by square of norm of u plus v. So by the definition of norm of u plus v, this will be inner product of u plus v with inner product of u plus v, and so using the properties of inner product, this will be inner product of u with u, plus we will have inner product of v with u and inner product of u with v, so that will be twice inner product of u comma v, as inner product of u comma v is equal to inner product of v comma u plus inner product of v comma v. Now inner product of u comma u is norm of u square, and as u and v are orthogonal, their inner product is 0, and so we have square of norm of u plus v is equal to square of norm of u plus square of norm of v. So this proves the generalized theorem of Pythagoras. So now we go to the next slide. So let us take a particular example. We have considered the vectors x and x square of p2. So norm of p is norm of p will be square root of inner product of p with itself, and that will be integral -1 to 1 x square dx. So x square is the even function of x, and therefore this will be 2 times integral 0 to 1 x square dx inside square root, and that will give us square root of 2 by 3. And similarly, square root of q, that is norm of q, that is square root of inner product of q with itself, and therefore simplifying it, we have its value square root of 2 by 5. So these are norms of the vectors p and q. We will use them in further session. So inner product of p and q here will be integral -1 to 1, and integrand is x into x square. Integration is with respect to dx. So this is integral -1 to 1 x cube dx, because x cube is odd function of x and integral is -1 to 1, so this becomes 0. Thus from Pythagoras theorem, we have for these polynomials p and q which are orthogonal with this given inner product, we have Pythagoras theorem. According to Pythagoras theorem, square of norm of p plus q is equal to square of norm of p plus square of norm of q, and therefore that will be square of square of norm of p plus q, that will be equal to square of norm of p plus square of norm of q. See in previous slide we have obtained the norms of p and q, and we are using them here. Okay, and so the answer is 16 by 15. We can check this result by direct integration. Let us go on Teletop and see the result by direct integration. The given vectors are p equal to x and q is equal to x square in the inner product space p2. So here p plus q will be x plus x square, and so the inner product of p plus q with itself, that will be equal to integral -1 to 1 of x plus x square into x plus x square dx, So that will be equal to integral -1 to 1 x square plus x cube plus x cube plus x raised to 4 dx. Now see here, there is an even function of x, there is odd function, even function, and so term by term integration, on term by term integration we will have integral of this term 0, integral of this term 0, and we have integral of this term equal to twice integral 0 to 1 of x square dx plus twice integral 0 to 1 of x raised to 4 dx. Okay, and on simplification we have this is equal to 16 by 15. So this is inner product of p plus q with itself. Okay, and so this is norm of p plus square of norm of p plus q actually, right? And so it is also 16 by 15. So this is how we can check we have checked this result by direct integration. Now we go to orthogonality of inner product space. Let W be a subspace of an inner product space V. So V is an inner product space and W is its subspace. So W is a vector space itself and it is a subset of vector space V. Now a vector U in V is said to be orthogonal to this subspace W if it is orthogonal to every vector in W. That is, if U is orthogonal, if inner product of U with every vector of W is 0, then we say that U is orthogonal to every vector in W, and the set of all vectors in V that are orthogonal to W is called the orthogonal complement of W. So let us see again. So if U is a vector of V which is orthogonal to every vector of W, then we collect such vectors of V and set of such vectors V in W in V, capital V, that are orthogonal to all vectors of W is called orthogonal complement of the subspace W, and it is denoted by W perp. In geometry, this symbol is used to indicate perpendicularity, and it is spoken W perp. Now properties of orthogonal complements. So if W is a subspace of finite dimensional inner product space V, then the orthogonal complement of W, first property is W perp is a subspace of V, means W perp, because the elements of W perp are from V, so it is subset of V. Moreover, it will satisfy all properties to be a vector space with those operations under which V is itself a vector space. So W perp is a subspace of V. Next property is the only vector common to W and W perp is 0. That is, W intersection W perp is 0. And the last property is the orthogonal complement of W perp is W. Means if W is a subspace of vector space V, inner product space V, then its orthogonal complement is W perp, and orthogonal complement of W perp is again W itself. So perp of W perp is W. So by the last property, see, W and W perp are orthogonal complements of one another, and so in general we shall say that, in general language we shall say that W and W perp are orthogonal complements. Now the fundamental theorem that provides a geometric link between the null space and row space of a matrix is, before going for this result, what is null space of a matrix? So null space of a matrix, say matrix A, an M by N matrix A, is the solution space of the system of homogeneous linear equations Ax equal to 0, and the row space of a matrix is the space generated by row vectors of matrix. And so the result is theorem: if A is an M by N matrix, then the null space of A and the row space of A are orthogonal complements in Rn with respect to the Euclidean inner product. Okay, and the next is the null space of A transpose and the column space of A are orthogonal complements in Rm with respect to Euclidean inner product. Here transpose of matrix A means transposing all the rows of matrix A to the columns of in new matrix to the columns means બધી જ હરને સ્તંભમાં ફેરવતા જે નવી મેટ્રિક્સ મળે એ મેટ્રિક્સમાંથી એને A ટ્રાન્સપોઝ કહેવાય છે. ઓકે, સો નલ સ્પેસ અગેન I repeat, the null space of matrix A is what? The null space of matrix A is the solution space of the system of equations Ax equal to 0. Next is also theorem, equivalent statements, and there are many statements here, but you need to note down them if possible, because these are very important and this is conclusion of all the results till now. So it is, if A is an m by n matrix and if TA from Rn to Rn is multiplication by A. Here in particular let us take square matrix, let us take A as an n by n matrix. So let us take matrix A with its order n. Then TA is a linear transformation from Rn to Rn and it is defined by multiplication by A. Then the following are equivalent. So now A is a square matrix of order n. Then the following statements are equivalent, means one implies the remaining all. Any one of them implies the remaining all, and it is actually double implies. So first is A is invertible. It is equivalent to Ax equal to 0, has only the trivial solution. The reduced row echelon form of matrix A is identity matrix of order n. Next is A is expressible as a product of elementary matrices. Next is Ax equal to B is, this is a system of non-homogeneous equation and it is consistent for every n by 1 matrix B. All these are equivalent to determinant of A not equal to 0. Ax equal to B has exactly one solution for every n by 1 matrix B. The range of TA, the transformation that we have defined earlier, TA from Rn to Rn defined by multiplication by matrix A is Rn. The range of TA is Rn. This transformation TA is 1 to 1. The column vectors of matrix A are linearly independent. Also the row vectors of matrix A are linearly independent. The column vectors of A span Rn. That means if we take span of column vectors of A, that will be Rn, also they are Li, so they will form basis for Rn actually. The row vectors of A span Rn. Next is the column vectors of A form a basis for Rn, and the row vectors of A form a basis for Rn. These all are equivalent to say that A has rank n, to say that A has nullity 0, to say that the orthogonal complement of the null space of A is Rn. The orthogonal complement of the row space of A is 0. Okay, so I would like to show these slides once again. These equivalent statements, they are very important. So we go for the next topic, orthogonal and orthonormal sets. A set of vectors in an inner product space is called an orthogonal set if all pairs of distinct vectors in this set are orthogonal. Means if we consider a set of vectors say v1, v2 up to vn and vi comma vj, the inner product of vi and vj is equal to 0 for all I not equal to j, I and j vary from 1 to n, then this set of vectors is called an orthogonal set of vectors. Similarly, we define orthonormal set of vectors. It is orthonormal set. An orthonormal set is an orthonormal set of vectors is a set of vectors in which each vector has norm 1. Okay, or we can say that an orthogonal set in which each vector has norm 1 is called orthonormal. So to check whether a set is set of vector is orthonormal or not, first we should check whether it is orthogonal or not. If it is not orthogonal, it cannot be orthonormal. So to a set be an orthonormal set, the two conditions are, first it should be orthogonal set, and second condition is norm of each vector of this set must be equal to 1. So let us take an example. Let u1 equal to 0 1 0, u2 equal to 1 0 1, u3 equal to 1 0 minus 1. These are vectors of R3, and we take the Euclidean inner product space. We consider Euclidean inner product space. Then you can see with Euclidean inner product space, these vectors have inner product 0, u1 inner product of u1 u2, inner product of u1 u3, inner product of u2 u3 are all 0. And so the set of these vectors, say S equal to u1 u2 u3, is an orthogonal set. Here the Euclidean norms of these vectors, the considered vectors are, the norm of u1 is 1, norm of u2 is root 2, norm of u3 is equal to root 2. We have considered Euclidean inner product, remember that. So S is not an orthonormal set. Why not orthonormal? Because the norm of the vectors u2 and u3 are not equal to 1. But this is not an orthonormal set, but we can generate an orthonormal set from it. So let us see how. So the process of multiplying a non-zero vector by v by its length is, to obtain unit vector, is called normalizing v. How?